Hi, welcome to this overview of differential geometry. In this video, we'll go over concepts like manifolds, smooth functions, tangent spaces, vector fields, differential forms, and finally integration. This is meant to be a short video surveying the big picture of differential geometry, so naturally a lot of details are going to be swept under the rug. However, it would still be helpful to have an understanding of at least single variable calculus, just so you can fully grasp the concepts in this video. Before we begin, let's go over a brief history/introduction of differential geometry. Bits and pieces of the modern theory of differential geometry can be traced as far back as ancient Egypt. In fact, there are even written accounts of this stereographic projection, which is the projection of a sphere onto a plane, from as early as 2,000 years ago. This particular projection came in very handy to cartographers for drawing maps of the world. But the modern theory of differential geometry, given in the language of calculus, didn't come around until after the 1600s. In essence, the subject started off with the question of how one can do calculus on curvy things instead of flat things. You might be wondering what that even means. To get an idea of this, let's go back to single variable calculus for a moment. Here, the overarching goal was to somehow measure how much area is under this curve. We did this by dividing the baseline into smaller regions and by assigning to each region an approximate value of our function. And then we summed over all of these regions and we got the area of this curve. Notice, however, that this curve is just a visual aid. We can get rid of it and think of the integral as assigning to each of these intervals a value or a weight and doing a weighted sum over all of these intervals. This is the definition that can now be easily translated to curvy things, which I'll start to refer to by their proper name, manifolds. For any manifold, what we want to do is a weighted sum over small regions on the manifolds. Immediately though, one runs into a lot of problems. The biggest one probably is, how do you even measure the area of a region on a curve? Intuitively, we could think of it as that if you zoom in close enough, then the manifold simply looks like a surface. As an example, we live on Earth, which is a sphere, and yet for most purposes, locally, we can approximate it as a flat object. The task then is to somehow express this idea mathematically, and we'll start by writing a definition for manifolds that will allow us to exactly do this. We require that a manifold be an object that can be covered by patches, each of which come with a function that maps the patch to a surface, which is the two-dimensional real coordinate space in this case, but in general it's the same dimension as the dimension of our manifold. This is key because this will allow us to restrict whatever problem we're solving to a local problem, which we can then transform to a problem in multivariable calculus and then exploit the existing techniques we have there. The next step that we'll be making is to define something called a tangent space. This is a space at every point which can be visualized like this plane on this manifold. The word tangent should be reminiscent of single variable calculus, where the tangent was the velocity of the curve at some point. However, we can't define it in the same way here, because the problem is, at no point in our definition of a manifold did we indicate that it was living in some larger space. The manifold is all that there is. The space around it doesn't exist, and so it doesn't really make sense to talk about vectors, because that implies the existence of a vector space in which the manifold is placed. So we can't define the tangent space using vectors. What we can do is use smooth functions. The smooth functions that we'll be dealing with here are very similar to the ones that you may have encountered in calculus classes. One has to face the task of translating the smooth functions that we are familiar with from real coordinate spaces to manifolds, but this entire process is an exercise in exploiting the patches that we defined earlier with our manifold. In short, a function on a manifold is smooth if it's smooth in the normal sense on this flattened patch created by the function that comes with the patch. The way that we're going to use these smooth functions is by taking their directional derivative. If you're unfamiliar with the directional derivative, then note that it's just the derivative of a function in a particular direction. This is something that you'll learn in multivariable calculus when you are faced with the task of defining what a derivative means on a surface, since we don't even have a direction to differentiate with respect to. We observe that if we take the directional derivative of a function with respect to all possible curves from the real line into the manifold, then we'll be getting this same tangent space that we earlier wanted, because the directional derivative encodes the information about the velocity vector within its expression. With this, we have our tangent space. Now, the reason why we introduced all these tangent vectors is to take another step towards defining an area. Indeed, the parallelogram generated by any two tangent vectors on any given point is analogous to the definition of the infinitesimal interval in single variable calculus. To get to that, though, we must first note that our integral will be over a region, not a single point, so we somehow have to put together these tangent vectors, and we do that in the simplest possible way we can do it. We simply put them together and call it a new mathematical object. This is precisely what vector fields are. We do require that the field be smooth, which formally means that at any point the corresponding tangent vector is smooth at any function that we evaluate it on, but could be thought of as the vector field flowing in a generally nice way, without sudden deviation or changes. Let's stop for a moment now and observe that we have a setup that allows us, at least pictorially, to define an area at every point given by some collection of vector fields, where the area is the parallelogram generated by the tangent vectors at this point. Mathematically, though, we need something that can take this collection of vector field and spit out a number. This leads directly to the definition of differential forms. Differential forms are objects that take in vector fields and return numbers. Although I've been drawing mostly two-dimensional manifolds in this video, our theory is defined for general manifolds, and the consequence of this is that we have to construct these differential forms in such a way that they can take in any number of vector fields, depending on the dimension of the manifold that we're working with. We also want it so that the forms evaluate to 0 if two tangent vectors are the same, because if two tangent vectors are the same, then this area just collapses and any working theory should give a 0 here. Indeed, differential forms are defined just this way. A differential form looks like this. Each of the di's that you see here are differential forms in their own sense. This symbol here in the middle is called the wedge product, and it helps us combine two differential forms to make a new one that would act on more vector fields. This d here is also something worth noting. It's called the exterior derivative, and it's another way we can build higher dimensional differential forms. In fact, the vector calculus operators divergence, grad, and curl, which you may be familiar with, are all special instances of this d operator. One final thing to mention is that we'd like to do integrals, so it'd be somewhat useful to be able to put actual functions somewhere that we can integrate over, and we make that a thing in our definition for differential forms as well. Giving formal definitions for forms and the exterior derivative is quite complicated, and I'd say even requires a very good formal understanding of everything we've defined so far, so I won't go over them over here. Importantly though, we now finally have a notion of area, something we can integrate on a manifold. We've developed a lot of stuff so far, and came across probably a great number of new concepts. This might be daunting, and it certainly takes quite a while to develop, as you'll see if you ever take a course in differential geometry. The payoff, however, is that when we actually reach the point of defining the integral, you'll see that we have developed everything just so that it makes sense. Now we can simply take the integral of a differential form over some region in our manifold, and once we've written this down, we can simply use the patch around this form, switch to stuff that we know how to integrate, and evaluate the results. It's possible that your form is not contained in a single patch, and in this case we introduce things called partitions of unity, which allow us to stitch together these patches and sum over all of them. There are some other subtleties. For instance, you can only integrate an M form over an M-dimensional manifold, nothing less, nothing more. Another one is that this construction only applies to forms which are contained in a compact set, and you could think of this as meaning that we require the form be contained in only finitely many of these patches. One final result that just can't be missed from this video is Stokes' theorem. Stokes' theorem is one of the most beautiful results you can get by developing this entire theory. It basically says that the integral of the form over the boundary of a region is the same as the integral of the exterior derivative of the form over the entire region. In single variable calculus, this simplifies this fundamental theorem of calculus. In higher dimensions, one way to think about this is that it says that over any region, the sum of the changes over the boundary are the same as the sum of the changes inside the region. Basically, if you've got a few swirly things going on here, then the sum of the swirl inside is the same as the sum of the swirl on the boundary. It's really an amazing fact, and that's not even mentioning how many amazing applications this has. Nevertheless, this brings an end to our entire construction. I'd like to note that I skipped over a huge amount of detail, and I didn't even cover things like submanifolds, orientations, closed and exact forms, tangent maps, and many more things, because it's hard to present everything that differential geometry covers in a single video. However, if you are interested in learning more about this, then I'd recommend reading a textbook on differential geometry or taking a course in it. Thank you, and I hope you enjoyed the video.